Reinforcement learning isn't just an algorithm, it has a very beautiful mathematical basement. I'm a student studying computer science in the University of Bonn in Germany, and I've just finished an exam about robot learning. So before I forget all of it, in the next couple of minutes, I talk about the mathematical formulation of its components. Well, in this video, which was my first video about reinforcement learning, I talked about what I know about it, its components, one of its trade-offs, and all types of AI models. At the end of it, I told you that
A simple implementation of an RL model.
But I thought it's better to know about its formulation before starting to implement it. I was studying for my exams for like 2 or 3 weeks, and I know a lot of mathematical stuff right now, but not for long. All right, first off, let's talk about return. Remember the agent, which can be our robot, something which traverses throughout the whole environment. The main goal of this robot is to collect as much reward as possible. So this return thing should be maximized. Its equation is, it is shown by g, for example, g at the time t, which is equal to lambda reward at in t equals plus reward 2 at t plus 1 and until the end of time. This lambda is called discount factor, and it is between 0 and 1. Since it's between 0 and 1, as time goes by, it gets smaller and smaller. This is because we don't want to care about the reward in very future time. Reward is a property of the environment. We can't control it, just remember it. How do we do it? We keep a map which shows the rewards in the environment. Those maps are called value functions. We have two types of value functions. Let me show you for it, which is value functions. The first one is state value function. And the other one is action value function. It is shown by we keep it for each state, which is the expected value of our maximum return when the state of the agent is equals to s, which we want to keep it here. Action value maps the state action pair to a reward. It is shown by q. As I said, it is for state and action, which is equals to expected value of maximum return if the state is equal to s and the action which robot chooses is equal to a. Well, I want to give you a little intuition about this. Consider this is our environment. Sorry, this is our environment. And the robot traverses here. And one of these is our state. And well, the reward is, for example, 5 here. In this state, we have 4 actions, 4 options, which is here, here, right, and down. And consider that for each one of these actions, we have, for example, 4, we get 3 here, we get 2 here, and we get, for example, 6 here. I mean, the right movement is the best choice. So here we have, and consider this is s. Here we have the value state of s is equals to 5, and the value state of up is 4, q of s down is 2, and so on. So here we see an expectation function. You may not be familiar with this, so let me define it here. The expectation function of x, consider that x is a set of smaller x, x1, x2, 2, xn. So it equals to the sum of, for each member, this member, for example, from 1 to n, the member multiplied to its probability, the p of xi. Well, this is the discrete format of this equation. We have a continuous format too, but I don't want to use it right here. You see a probability here. What does it mean? I mean, aren't we sure that, for example, when we're in the state t, when we are here, aren't we sure that where are we going to go? No, we're not. We don't know everything about the environment. We only know probabilities, so we should use them in our calculations. The next thing is policy, but before that, I really appreciate it if you support my channel. Your support gives me the energy to keep creating contents like this. And yeah, based on this value function, based on this map, the agent decides where to go. So policy is our movement in the environment. It's the decisions that the agent makes. More specifically, it maps out different states to actions which we take. Well, in the beginning, of course, we don't know what to do, so our policy isn't optimal. There are a lot of formulas for policy, but I just want to show you a little annotation about it. Oh, it's too. Let me bring this. Well, policies are normally shown with P, and the optimal policy, which we get to at last, is annotated with P star. The whole point of the algorithm is to find this one. The next thing I needed to know in reinforcement learning was Bellman equations. Value functions are somehow memory which shows places in the environment which have reward. So we don't have them at the beginning, so we have to figure them out. We have to compute them. Well, figuring this out is tough because to get the reward for every state in the environment, you need to calculate the entire return, which you see here. That's a random episode. That's pretty much impossible. There are way too many episodes. For example, this one, this one, this one. And even if you had just one episode, it would still be super expensive to go all the way to the end. So Bellman's idea was simple. Instead of looking at whole future, just use the next step so you can compute it recursively. I don't want to talk about its proof or intuition. I go right straight to the formulas. So let me erase this one. Go away. So Bellman's, well, since we have two value functions, one of them with v and one of them with q, we have two equations for Bellman. So for state value, we have the value of state s is equals to the reward at the time t plus 1, discount factor, and the value of state at time of t plus 1 if our current state is s. And for the action value, this is still here. State action equals to the reward at time t plus 1, the discount factor of t plus 1, and the action of t plus 1 if the state is s and the action is a. So as you can see, this is the at next state, as well as this one. And this is our current state. That's, wow, so crooked. These equations lead to very important algorithms like dynamic programming, Q-learning, and value iteration. They are really a key point. Bellman also had some optimality equations, which let me show you here. I don't want to talk about them too much, so just make a little change here to show you the result. Bellman, this one, which is Bellman's optimality. So we show them with star, which means that they are optimal. They are value functions, they are maps which we want to get eventually. And this one is, let me try it with black. The maximum of for each action, Q star, which is here, of state S per A. And this maximum is for that we have multiple actions, for example, A1, A2, for example, A3. This one leads to, for example, 2, this one leads to, for example, 5, and this one leads to, for example, 12. And this maximum operator chooses this one, or something like that. And for this one, we also have something like this. I mean, for example, we should bring it something here, which is maximum per AT plus 1, which is the star itself. It may have got a little bit complicated, especially the optimality equations. In the next video, we implement it and we can picture all of this way better. There are lots of ways for having a policy, for having a value function. We have algorithms like Q-learning, policy gradient. It's a whole branch of knowledge. This was it, guys. Hit the like button if this video might help you. Be curious and keep learning.